Hello everybody, my name is Leonardo Leslie. I'm from Group 3 and today we'll be presenting the Data Envelopment Analysis or DEA for short. And these are my group members, Lo Wikit, Aryu Farhana, Firda Hariri, and Muhammad Aidit Daniel. This is going to be the contents of our video. So first off, it will be introductions. I'll be responsible for it. And second and third, we'll look at example 1 and example 2. That will be for my other teammates. So what is DEA? DEA is a comparative technique to evaluate the relative performances of organizations or producers. The application of DEA is mainly used for evaluation of non-profit or not-for-profit organizations. However, DEA can be utilized in other situations competing with other techniques as cost-benefit analysis or multi-criteria decision making. So for example, in 2005, to determine the best choice for traffic planning, considering the design and the location of a highway in Memphis, DA was used for that study. So why is DA so suitable for these types of evaluations? Well, it's because DA enables results to be compared while considering allowances for factors. DA enables us to determine the efficient and inefficient units within a given framework where the results are considered in their given context. In addition, information gathered from the DA assessment can allow us to compare each inefficient units with its peer groups. That is a group of efficient units that are identical with the units under analysis. So success factors within the role model units can then be extrapolated by studying it, and the comparable units can then follow these success factors to ensure success. Emmanuel Tanasolis, a professor of management sciences, argues that DA is more superior compared to other methods like regression analysis due to it being able to contextualize results. In this video, our focus is on a model proposed by Charnes, Cooper, and Rhodes, or CCR, what we call CCR model. And in DA, we also make sure that the organizational units that are to be assessed needs to be relatively homogeneous. Next, the units are now termed as decision-making units, or DMUs for short. A considerably large set of units is preferable for the DEA assessment, as the whole technique is based on comparison of each DMU with all the remaining ones. This ensures that the assessment will remain meaningful. We assume that each DMU produces n outputs by means of m inputs. Numerical data are available for each input and output, with the data assumed to be positive for all DMUs. The input, outputs, and choices of DMUs should reflect an analyst's or a manager's interest in the components that will enter into the relative efficiency evaluation of the DMUs. In principle, smaller input amounts and larger output amounts are preferable, so the efficiency scores should reflect these principles. Lastly, the measurement units of different inputs and outputs need not be congruent. Some may involve number of people or areas of floor space, money expended, etc. This is going to be the steps for DEA. So for each DMU, we form the virtual input and output by using weights VI and UR. So this is going to be our virtual input and outputs formula. Then we try to determine the weight using linear programming as to maximize the ratio, and just use this formula. Okay, using the data, we measure that the efficiency of each DMU once, hence need n optimizations, one for each DMUJ to be evaluated, and let the DMUJ be evaluated on any trials be designated as DMU-O, where O ranges from 1 to n. We solve the following fractional programming problem, so not linear, to obtain the values for the input weight, which is VI and UR as variables. So this is going to be our general formula, and we're going to derive the linear programming from this formula. Okay, so now we're going to replace the fractional program to a linear program. So to do this, we set the denominator is 1, and you get this linear program. And regarding the CCR efficiency of DA, DMU-O is CCR efficient if the theta equals to 1 and there exists at least one optimal V star U star, with V star being more than 0 and U star also being more than 0. Otherwise, the DMU-O is CCR inefficient. This is for the input-oriented CCR model. So you notice that it's maximized here, and we use UR and YRK as the variables here. And over here, it's VI XIK equals 1. And next, this is output-oriented CCR model. It's different from the input. Input is maximized. This is minimized. And you use VI XIK as the variables. And over here, you just replace it with YRK equals 1. So we're going to go to the next section, which is the examples, to further understand how to use these steps practically. And I'll pass on to my next team member. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Adidini Bamakusairi. I am going to be showing you guys the first example. Okay, so what we have right here is the bank branches with one input and one output. The input is the number of staff employed and the output is the transaction process. Okay, so firstly what we gotta do now is do the input oriented CCR model. Okay, so this is the formulation on how to do the primal model. Okay, so this is what I got based on that formulation. So these are all the DMUs: the Birmingham, Glasgow, Cardiff, Leeds, London, and Manchester. Okay, so that's basically on how to do the primal CCR model. Okay, so next I'm going to be showing you guys how to solve it in the solver. Okay, so let's complete the table with all the data. Okay, so the input and output, weighted output, put it as the same as the output, and weighted input, put it the same as the input. This is for the startup. The value will change after we done the solver. The efficiency and the working. The efficiency is actually the value of the weighted output divided by the weighted input. And the working is actually the value of the weighted output divided by the weighted input. Okay, so that's basically how to complete the table. Next, for the weight input and weight output, you put it as 1 before you do the solver. The value will change after we do the solver. Okay, so first but not least, start the solver. The objective is actually for the primer is the weighted output. For this case, it is Birmingham. So we put the Birmingham D3 as the objective. Set it as the maximization. By changing variable cells is the weight input and output. Both of these, okay. Next is the constraint. The constraint is actually the weighted input. For this case, it is Birmingham. So the weighted input for Birmingham, which is 16, equal to 1. And then the next constraint is the working for all the bank branches from Birmingham to Manchester will be less or equal to 0. Okay, so that's it for the constraint. The solving method is by simplex LP. Okay, so that's how to do it. Then just click solve. Okay, so I have done the solver. So this is what we get. The values for the table has changed. The efficiency for the Birmingham is 0.45714287. Okay, so that is the CCR or the optimal solution for the Birmingham. Next is the weight for the input and output. So now right here we have the weighted input and the weight output. Okay, so Birmingham, the input is 0.0625 and the output is 0.074143. Okay, so that is 1 for the Birmingham. Okay, so these are all the Excel solver that I have done for all the other DMUs. We got different values for the input and output. Okay, so this is the summarization for all the CCR of all the bank branches. Okay, so we have ranked it as number 1 from 1 to 6. Okay, so the first one is the Glasgow with the CCR equal to 1, which is the most efficient between all the other bank branches. Okay, so that's it for the primal IP model. Next, I'm going to be showing you guys the second part, which is the dual model for these bank branches. Okay, so this is the formulation for it. We've minimized for the input model. Okay, so these are all everything that I have done. I'm going to be showing you guys the first one, which is the Birmingham. Okay, so basically the model of dual is a transpose of the primal model. Okay, so the constraint, as we can see right here, is the first one is actually the value for the output of the bank branches. The next constraint is actually the values for the input. Okay, so that's it from me. Thank you.
Hello, my name is Loikit. I'm going to explain the graphical analysis, female and dual output-oriented CRR model for example 1. Let us begin with the graphical analysis for example 1. We need to investigate our problem first before we start to plot our graph. From the table shown here, we know that this questions only one output and one input, so we're able to use the single input and single output cases of graphical analysis in this example. Before we start to plot our graph, we need to calculate the output per input. For this, we need to divide our output for each branch by their input. The tables in the Excel show that the highest output per input is Glasgow, while the lowest output per input is Birmingham. This implies that the Glasgow is the most efficient branch and Birmingham is the least efficient. We may use the scatter functions in Excel to plot our graph. To plot our graph, we will let X become the input while Y become the output. Here is our result. For the point I mentioned just now, we know that the Glasgow is the most efficient branch, so the frontier line is connecting from the origins to the point of Glasgow. By simple calculations, we know that the efficient frontier line is y equals to 8.75x. To plot the efficient frontier lines, we may calculate the efficient frontier line point for each x, which is the input in the table. Same method to input this data, we're going to apply the frontier line point for each x. In this case, we're going to apply the trendline functions to draw the frontier line. We may hide the efficient frontier points to make our graph become tidy. The point which is the most efficient branch, Glasgow, is lie on the efficient frontal, while another point lie below the efficient frontal. Then we may measure the efficiency for every branch we left to Glasgow. Next, I'm going to discuss the output-oriented CCR model for example 1. Here is the output-oriented CCR models for the K terms. V is the weight of their input, while X is the input value. U is the weight of their output, and Y is the output value. The objective is to minimize the data by changing the value of V, which is the weight of input. Here is the constraint. I will only show one example, which is Birmingham, and the same methods we may apply to another branch in Excel. By applying the outputs-oriented CCR models, here is our CCR model for example 1, Birmingham. We're going to apply the data solver to solve this DM yield. First, we put our CCR models Birmingham in this table, while the weighted output is V times the output with their wave, and the weighted input is V times their input with their wave. The efficiency is divides the weighted output by their weighted input, while the workings is the constraint from here to here, which is we use the weighted output to minus our weighted input. the set objective column here, we will put the weighted input for the bringing pump. Choose minimum and then changing the variable cell is the weight of the input and output. While the constraint is this, which is the weighted output equals to 1. While the workings also need to be less or equals to 1. And then tick the make constraint variable non-negative, choose the simplex linear programming as our solving method, then solve the CCRO model. Here is our optimal solutions. For this example, the efficiency, which is delta, equals to 0.45714. So it is CRR efficient because the data does not equals to 1. Here is our summary for output-oriented CCR models. From here, there are only one CCR efficient with this gas code because the data is equals to 1 and no zeros found in the weight for input and output for gas code. Here is the range of this example. Lastly, I will talk about the dual output-oriented CCR models. Here is the dual output-oriented CCR models. By just applying the dual methods to the primal output-oriented CCR model, we just applied the dual to solve this primal CCR model to get the dual output-oriented CCR model. Here is the example after applying the dual output-oriented CCR model for the first examples, which is Birmingham. We can apply this CCRO model to rest of our runs to get their dual output-oriented CCR model. That's all for my part. Thank you.
Assalamualaikum and hi, my name is Aifahana binti Amri Hamzah. Today I will be presenting for example 2. So this is the question where we have a set of 4 car garages with 2 inputs and 2 outputs. The 2 inputs are staff number and showroom space, while the 2 outputs are the number of sold cars and profit. And this is the data given. I will be using the Prima Multiplier CCR model for input oriented. And for example, for DMU Winchester, this is the objective function and the constraint for the car garage. And by referring this constraint and objective function, I can actually calculate the efficiency for this car garage by using the Excel. So after you key in all the data in this Excel, you need to calculate the weighted input, the weighted output, the efficiency, and also the working. So for the weighted input, is actually the addition of input multiplied by its weight. So say for here, 7 times 1 plus 8 times 1, we got 15. So for weighted output, it is the addition of output multiplied by its weight. 2 times 1 plus 1.5 times 1, we got 3.5. Efficiency is the division of weighted output and weighted input. So here we got 3.5 divided by 15, we got 0.2333, and so for the working is the subtraction for weighted output and weighted input. So actually we can assume the weight for each of the output and input to be 1. So let's say we want to maximize Winchester. So here we will use solver. So after you click the solver, this will appear at your computer. So the set objective. So referring back to the primer, the set objective is actually the weighted input. So here the weighted input for Winchester is 3.5. And we choose the maximize. And what is the variable cell that we want to change? It is the weight. So we choose all for weight over here. So the constraint is actually the weighted input for Winchester. We need to be equal. It is need to be equal to 1. And the working, all the working here is actually less than or equals to 0. So when we solve it, this is the answer. So we got the efficiency for Winchester is 0.80357 or 80.36%. So I already did for each of the car garage. So for max handover, we got the efficiency for 100%. For maximize benzene stock, it is also 100%, and for the maximum pool it is 79.17%. So it is how I calculate the efficiency for output by using that solver in Microsoft Excel. Thank you.
Assalamualaikum and hi, my name is Firda Hariri. Now I'm going to proceed with example 2, which have two inputs and two outputs. Before this, we already did the primal CRR model. So from that primal, we can compute the dual envelopment analysis. So to compute the dual, we're going to let lambda 1, lambda 2, lambda 3, lambda 4, lambda 5 be the dual variables. So we get that lambda 1 is for Winchester, lambda 2, Andover, lambda 3, Basingstoke, lambda 4, pool, and lambda 5 is the input constant here. So to compute the dual, we're going to make the constraint where the first constraint for the dual are from the U1 of primal. So the U1 for primal will get 2 lambda 1 plus 2.3 lambda 2 plus 0.8 lambda 3 plus 2.6 lambda 4 greater and equals to 2. So we get that from the objective function from the primal. The next one is from U2, and that making 1.5 lambda 1 plus 1.6 lambda 2 plus 0.5 lambda 3 plus 1.9 lambda 4 greater and equals to 1.5, which we get from the objective function of the primal. So same as the third constraint and fourth constraint, we get that from V1, V2. So we're going to let lambda 5 equal to theta, which is the efficiency. So we're going to have the dual LP as written as follow. We're going to change the negativity here, and then the symbol here, it will become less than and equals to 0 for the third and the fourth constraint. Okay, so we are going to have the same formula, same formula for the Andover, for the Basingstoke, and also for the pool. Okay, for the next one is for the discussion for example 2. Now we are maximizing the weighted input to produce the efficiency of the outputs. So for Winchester, when we maximize the input, we have the efficiency for the Winchester is 0.803571429, which is equals to 80.36%. So we need to understand that the DMU unit have classified into two, which is the first one is efficient and the second one is inefficient. Efficient unit is when the efficiency is equals to 1. So when it is inefficient, it is when the efficiency is less than 1. So we can see that here that Winchester efficiency is less than 1. So the CRR model here is inefficient. So when there is inefficient unit, we need to find the target value so that we can compare it to make the this garage to be efficient. So we are going to compare with Andover, which have the efficient CRR, which is the efficient CRR, which is 1, equals to 100%. So the next one is for Andover, which have the efficiency equals to 1. Now we can say that the CRR is efficient. So the next one is Basingstoke. You can see the efficiency for Basingstoke is 1. So we can say that the performance for Basingstoke is efficient, which is 100%. So the last one is for pool. You can see that the efficiency for pool is 0.791667, which is equal to 79.17. It is less than 1. So we can say that this garage is inefficient. So we are going to find the reference set, the target values to compare. So we can see that we need to compare with Andover, which have the efficiency of 1 equals to 100%. So why we need to find the target values, the reference set? Because this is in order to avoid to study all of the garage so that we can compare it with the highest efficiency. So that's all from us. Thank you.